to Math GPT. Today we're going to explore a fascinating connection between two seemingly different areas of physics, plasma physics and quantum field theory. Specifically, we'll look at how energy thresholds lead to the emergence of observable phenomena like plasma color and particle mass. Our journey will connect experimental plasma physics with the theoretical challenge of explaining mass in particle physics. Along the way, we'll explore how energy quantization creates observable structure in the universe. Let's begin by understanding wave-particle duality as the foundational state of matter. In quantum mechanics, all particles exhibit both wave-like and particle-like properties. This duality is fundamental to understanding matter at its most basic level. The de Broglie wavelength equation shows that any particle with momentum p has an associated wavelength lambda. The equation is lambda equals h over p, where h is Planck's constant. At very high energies, matter exists in a state where particles behave more independently, like in a plasma. As energy decreases, matter transitions through different phases, eventually leading to bound states like solids where mass becomes an organized, structured manifestation of energy. Now, let's focus on plasma, which is often called the fourth state of matter. Plasma is a gas that has been energized to the point that electrons break free from their parent atoms, creating a mixture of charged particles. This happens when sufficient energy overcomes the binding energy of electrons to nuclei. In a plasma, free electrons and ions move independently. When these free electrons recombine with ions or transition between energy levels, they emit photons with specific energies, which we perceive as light with characteristic colors. This creates what we call an emission spectrum, where each element has a unique spectral fingerprint. For example, hydrogen plasma emits primarily in the red part of the spectrum, while mercury produces a bluish light. These emissions occur only when electrons transition between discrete energy levels, following the equation E equals h times nu, where E is the energy difference, h is Planck's constant, and nu is the frequency of the emitted light. This brings us to our key concept: energy thresholds in plasma systems. In a plasma discharge tube, we need to apply a minimum voltage to excite the gas atoms enough to emit light. Below this threshold voltage, no light is emitted. As we gradually increase the voltage, we first see the gas begin to ionize, creating a plasma. Then, at specific threshold energies, different spectral lines appear as electrons make transitions between distinct energy levels. If we graph the light emission intensity versus applied voltage, we see a step-like function. Each step represents a threshold where a new emission line appears. These thresholds are what we call gaps of light, energy intervals below which certain excitations, and thus observable phenomena, do not occur. Now, let's make the conceptual leap to quantum field theory and the mass gap problem. In quantum chromodynamics, or QCD, which describes the strong nuclear force, we face a puzzling situation. The theory's fundamental particles, quarks and gluons, interact through massless gluon exchange. Yet, we never observe isolated, massless gluons. This is the mass gap problem. Despite the masslessness of gluons in the theory, all observable bound states, like protons and neutrons, have positive mass. There appears to be a minimum energy threshold, or gap, below which no physical states exist. This situation is similar to our plasma example, where certain light frequencies only appear above specific energy thresholds. In QCD, mass only appears once energy conditions meet critical thresholds. Let's now explore the deeper conceptual connection between these seemingly different systems. In both plasma systems and quantum field theory, we observe a fundamental principle: structured, observable phenomena emerge only above certain energy thresholds. In plasma, the organization of energy into discrete levels leads to the characteristic colors we see in discharge tubes or auroras. Similarly, in quantum field theory, the organization of energy through complex field interactions leads to what we perceive as mass. This suggests a broader principle of emergence in physics. Observable properties like color and mass aren't fundamental, but rather emerge from energy organization at critical thresholds. In conclusion, our journey from plasma physics to quantum field theory reveals a profound connection between seemingly different phenomena. Both systems demonstrate how energy thresholds lead to the emergence of observable structure, whether it's the colorful glow of a plasma discharge tube or the mass of particles like protons and neutrons. This conceptual bridge between experimental plasma physics and theoretical particle physics provides valuable intuition for understanding the quantized nature of physical reality. The implications extend beyond these specific examples to a broader principle. Many observable properties in nature aren't fundamental, but emerge when energy organizes itself at critical thresholds. By recognizing these patterns across different scales and systems, we gain deeper insight into the underlying unity of physical laws and the structured emergence of our observable universe.